Welcome to a second video on L'Hopital's rule. Let's go ahead and do a quick review before we look at our additional examples. L'Hopital's rule uses derivatives to evaluate limits involving the following indeterminate forms. Even if the limit is not in this form, we can often manipulate the function to obtain a form where we can apply L'Hopital's rule. And this is what this video focuses on. L'Hopital's rule states that the limit of a quotient, as we see here, is equal to the limit of the quotient of the derivatives under special conditions, as we see here. The special conditions are described here. You may want to pause the video and read these. We did discuss them in the first video. Let's go and look at our additional examples. Sometimes logarithms can help rewrite limits before using L'Hopital's rule. The limit as x approaches infinity of 1 plus 1 over x raised to the power of x approaches 1 to the power of infinity, which is an indeterminate form, but it's not in the form where we can apply L'Hopital's rule. But we can use logarithms to help. So if we set this limit equal to y, and then take the natural log of both sides, we'd have natural log y equals natural log of the limit and the natural log of this limit is equal to the limit of the natural log. So we have natural log y equals the limit natural log 1 plus 1 over x to the power of x. And now if we apply the power property of log, we can move this x to x times the natural log. So let's go ahead and do that. Now let's take a look and see what happens to this as x approaches infinity. This goes to infinity, and this approaches natural log 1, which is 0. Well, infinity times 0 is still indeterminate, and it's still not in the form we need to apply L'Hopital's rule. So notice that we're multiplying by x. Instead of multiplying by x, we could divide by the reciprocal. Let's go ahead and see what that does for us. Again, we normally wouldn't do this, but dividing by 1 over x is the same as multiplying by the reciprocal, or times x over 1, which is the same as multiplying by x. Now the reason we want to do that here is, as x approaches infinity, the numerator approaches natural log 1, which is 0, and 1 over x also approaches 0. So now we have the indeterminate form of 0 over 0. So in this form we can apply L'Hopital's rule. Before we find these derivatives, let's just remember that 1 over x is equal to x to the power of negative 1. So looking at the numerator, we'll have to apply the chain rule here where u is equal to 1 plus 1 over x. So the derivative of natural log u is 1 over u times u prime, or 1 over 1 plus 1 over x times u prime. Well, the derivative of 1 is 0. The derivative of 1 over x, which remember is x to the power of negative 1, would be negative 1 x to the negative 2. And notice in our denominator we have x to the power of negative 1 as well, so that derivative would be the same, negative 1 over x to the negative 2. And now we can see this simplifies nicely. This over this would equal 1. So we have natural log y equals the limit as x approaches infinity of 1 over 1 plus 1 over x. Well, 1 over x goes to 0 as x approaches infinity, so we just have 1 over 1 or 1. Now be careful, we're not done here. We're actually trying to find this limit, which is equal to y. And we have found that natural log y is equal to 1. So we need to solve this equation for y. Remember, natural log is base e, so we have e to the 1 is equal to y. So our original limit is equal to e. And this is quite interesting because we just found a definition for the number e. Let's go and take a look at another one. Notice here we have the limit as x approaches 0 of a difference, and both of these fractions as x approaches 0 approach infinity. So we have the form of infinity minus infinity, which again is indeterminate, but does not fit the form for L'Hopital's rule. So let's go ahead and add these two fractions together and then see what we have. So this first fraction is missing the factor of e to the x minus 1. And this fraction is missing the factor of x. So our common denominator is x times e to the x minus 1. And I'm going to go ahead and multiply that out. We'd have x e to the x minus x. And the numerator would be e to the x minus 1 minus x. Let's see what happens when x approaches 0. We'd have, this approaches 1, so we'd have 1 minus 0. So our numerator is approaching 0, and our denominator is also going to approach 0 as x approaches 0. So in this form we can apply L'Hopital's rule. Let's go ahead and find the derivative of the numerator and denominator. Derivative of e to the x is e to the x. Derivative of 1 is 0. Derivative of x is equal to 1, so we have minus 1. Now here we're going to have to apply the product rule. It's x times e to the x. So we'll have the first times derivative of the second, that would be x e to the x, plus the second e to the x times the derivative of x, which is 1. So we have plus e to the x. Then the derivative of x would be 1. Now if we try to perform substitution in this form, we'd have 1 minus 1, that would be 0 in the numerator, and then in our denominator we would have 0 plus 1 minus 1, which is still 0. So this limit is still in the indeterminate form of 0 over 0, but remember we can apply L'Hopital's rule more than once. So let's go ahead and find the derivatives again. Derivative of e to the x is e to the x. Derivative of 1 would be 0. Here we have to apply that product rule again, so we have the first times derivative of the second, so x e to the x plus the second, which is e to the x, times derivative of x, which is 1, okay, plus derivative of e to the x, that's e to the x, derivative of 1 is 0. Now let's see what we have. If we try to perform direct substitution, we'd have e to the 0, that would be 1. And in the denominator we'd have 0 plus 1 plus 1. So this limit is equal to 1/2. I hope you found these additional examples helpful.